enough people to just get started here, and it'll be available on streaming later on as well. Okay. So welcome to the last session of BSCS. It's been a pretty crazy semester, so thank you all for bearing with us. Thank you all for dealing with all the changes that have had to happen. Hopefully, it's our last online meeting as well. I'm really hoping that next semester we can get back to things as normal at some point, maybe in October or November. Let's see when that happens. Okay. And thank you all for putting so much effort into all the homeworks and things that we've had this whole semester. We've had a crazy amount of work that we've done, and I really appreciate that. And to reward you, there is of course no homework for today's session. Today is just a fun, free session. Okay, and moreover, there's no final exam. So I hope you can focus your remaining time on your other classes. All right. So what are we talking about today? So first of all, I'd like to keep today's session rather short. We're not going to do 3 hours, okay? If possible, I'd like to get done in about an hour and a half so that we don't even really need to take a break. Okay, so we'll just try to get done and move on to other things, all right? Okay, so today I'd like to just kind of wrap up some odds and ends, mention a few tools and techniques and things. Nothing to be tested, just things that I think will be good for you to know after you've done this class, so you have some directions on what you could learn next in terms of computing. Not necessarily in terms of all of data science, but at least in terms of computing, all right? Um, so three things I'd like to talk about. One is I'd like to just quickly touch upon the topic of degrees of freedom. Unfortunately, I'm going to have to make it much shorter than I thought because a demonstration that I wanted to show for you is not quite working right now. But I'll spend most of my time talking about some aspects of coding in R and a little bit of time talking about high performance computing and trying to handle heavier computing loads and data sets and things like that. All right. Okay, so let's get started. So I wanted to, my initial goal had been to spend a little bit of time talking about degrees of freedom. Um, Unfortunately, there's a limitation with what I can show you today because the demonstration down here that I wanted to show you no longer works. It's not really online anymore. And I contacted the author of that, and well, if they can send me something later, I'll pass it on to you. But I'll tell you the gist. In just like a few seconds, I'll tell you the basic idea of what I wanted to impart to you, which is that over the semester we've always been looking at degrees of freedom, and for different formula we have like different degrees of freedom. Sometimes it's p, or maybe like the number of predictors. Sometimes it's like n minus 1, n minus p minus 1. There's all different types of expressions of degrees of freedom. And just to kind of to cut it short, essentially what I wanted to talk about is what are those trying to express. Um, and I'll try to explain what we're trying to get out with degrees of freedom from two perspectives. One is on how much data we have, and the other is the dimensionality of the problems that we're working with. Okay, and I'll keep this very short. So first of all, let's talk about data. When we have, like, let's say we have like a regression problem, right? And we have X and Y. Well, we have exactly 1 point of data. Well, that's all we have, all right? What's the regression line that should fit this point? Is there a regression line that would fit this point? Actually, here, an infinite number of regression lines could fit this 1 point, right? Any regression line running through this point, maybe positive, maybe straight, maybe negative. Every regression line could fit this point. And this is a situation where we have not enough information to even answer the question. Okay, so this is a situation where we typically say we have no degrees of freedom. We are unable to solve this problem. We're unable to come up with a relationship between X and Y. And one way in which we express that relationship is we say n minus r. We say we're trying to express one relationship, but we only have 1 point of data. And effectively, this means we have zero, we don't have enough information. We just say we have zero information to answer this question, all right? So sometimes when you see degrees of freedom expressed in terms of n and r, Well, the N usually tells you the how much data you have, and the R often tells you how many relationships you're trying to solve here, something like this, okay? Um, moving on. Here's another example. In this case, we have two data points, and we can actually put a regression line through it. And so do we have enough degrees of freedom here? Do we have enough information to solve this problem? This is an interesting situation where we can actually, if we were talking about regression, put a regression line through these two points. Is that good? Actually, it might be too good. We have only 2 points, so there's only one line we could put in there. Not having any error, you'll notice that this regression line has 0 error, is actually not a good thing. It tells us that we cannot really find any nuance or find any way of contradicting what we're finding. We have not enough information to contradict the relationship that is postulated here. All right, so this is called perfect fit, but perfect doesn't mean good here. Perfect is something bad here. It just tells us that we have just enough information to answer this question, but not enough to try to disprove this. So we can't really do any hypothesis tests or anything. We have no error available whatsoever. And in a situation like this, the degrees of freedom would be 2 points with one relationship and one. All right. And this is another example. Now we have a third data point. That's great. And now the line doesn't quite go through these 3 points, and that's a good thing. However, we still don't have that much information. We could we could find some error here, all right? However, the line can probably fit these 3 points fairly well. And we call this kind of a situation overfit, where we can somewhat fit this model. We have enough error to, compute standard errors and things like that. But without more information, the picture will still be too good. And um, and the situation we typically want is where we have a lot more points than the number of relationships we're trying to solve. All right. So one way of thinking about degrees of freedom is really asking, do we have enough data to resolve the relationships we're interested in? And not only to get an answer, but to give us enough information that we can try to disprove whatever is, if something is claimed. All right. So degrees of freedom in one perspective is really about how many observations or how much data do we have versus how many relationships we're trying to solve. All right. So this is one kind of expression of degrees of freedom, and altogether it tells us, do we have enough information, right? And here information really means the amount of data we have. There is another perspective of degrees of freedom, which is about relationships. All right. Um, and so earlier on in the semester, we asked this question about if somebody asked us to estimate, to guess some values of y, but we have no predictors, we have no x variables, how could we possibly predict a y variable if we have no x variable, right? And what we said back then is that a naive guess of y, a null model, would be that just predict the mean every single time, right? That's probably the best prediction of y you can have if you have no predictors whatsoever. And you notice here I haven't drawn data points, so it doesn't matter how many points of y we have. If we have no predictors, the best we can do is just guess the mean. All right. So another perspective of degrees of freedom is about how many dimensions of data do you have? Not just how many rows of data, how many points, but how many dimensions do you have, right? And here, oh, excuse me. So, excuse me. The more, the better. If you have one dimension, like you have an x variable, then now you can estimate, let's say, one beta coefficient. If you have two variables, you can estimate two beta coefficients, right? So here, degrees of freedom can be expressed in terms of dimensions, meaning how many dimensions of data do you have beyond the null model, where the null model is you simply have no predictors whatsoever. All right. So In essence, what I wanted to kind of convey today is that you'll see these expressions of degrees of freedom, and oftentimes is referring to the dimensionality of your data. Oftentimes it's referring to the number of rows of data. How many observations do you have? And oftentimes it's referring to both. It's referring to both the amount of data you have and the dimensionality of data you have. All right. I had a demonstration that I wanted to kind of run, but I can't run it today. So I'm going to really cut this discussion short. I know it's not very satisfying, but at least to give you a gist of something about degrees of freedom, in case you have absolutely no idea why we talk about degrees of freedom. All right. And the reason it's important is because whenever we kind of compute these variabilities or a lot of things, we want to kind of average it out by how much information we have. So that's essentially why we're often dividing the information we have by some number, the degrees of freedom, that's telling us how much information did we have to begin with. All right. So this is my quick and dirty discussion about degrees of freedom. If I can get that demonstration working in the coming days, I'll email that out. All right. Okay. But that's all I wanted to mention about degrees of freedom. Right. I'm going to spend the remaining time we have talking about some computational things. So I'm moving on. And I apologize, I'm going to be moving at a pretty fast clip today because I really am trying to get done in about an hour and a half or less if we can, because I've asked you all to come very late and I don't want to keep you here forever. All right. So next topic, I want to talk a little bit about functions. We've seen functions this semester. You've seen how to run functions. You've also worked on writing your own functions. So that's great, right? So you've written your own functions as well. Um, let's take a look back at this um, code for seminar that I showed you a long time ago. Last week. All right, so let's get this seminar library going. And so here I am. I'm defining my measurement model. And as I mentioned, it's all one big function, right? It's all one big function. And within that function, I'm calling other functions like composite and this interaction term, right? Um, Question, what does this composite function return? Okay, so when I run composite, well, and within composite, you see there's a multi-items function. So what is each of these functions returning? You're used to functions usually returning some kind of object of data or values or something like this. So for example, multi-items was a function that Seminar provides you that just does something really silly and easy. All it does is takes a prefix of a variable of some variables, takes a sequence of suffixes, and it just kind of like plugs them together, right? So that's all multi-items does. Okay. Um, and there's actually something interesting you can do, which is somebody once asked me, hey, could I, instead of using numbers, could I just use letters? Like, what if I wanted to be prep A, B, C, D, E, right? And surprisingly, well, maybe not surprisingly, we can do letters as well. By the way, letters is actually a variable in R. It comes predefined. It's already created for you when you open up R. There's something called letters, okay? And letters, let's say 1 through 4, gives you the first 4 letters. So what we could do is we could actually take multi-items and tell it, create for me some variables, beginning with prep and ending with the letters A through D. And this will create a vector of variable names for you, okay? So when we created the seminar library, my students and I, students coming out of this class, we had a lot of fun creating functions that will do some helpful things. It captures some behaviors, it captures some things that we want to do frequently into a named function, into a named behavior, all right? And what the return usually is like a vector, a list, something like this, maybe a data frame, all right? So that's what multi-items does. What does composite actually return? You'll notice that composite also returns a vector, all right? And it's a strange looking vector. It's meaningful to the seminar package. It may not be meaningful to you, but it's essentially the construct name and the item names and something, some letter after it, A or B, repeated as many times as there are items. All right. And this is, however, returning a vector of type character. I've also, this vector actually has multiple types. It's a character vector, it's a construct vector, it's a composite vector. It's a vector of different things, all right? So this returns a vector. So in any case, whenever you're typing functions, you're usually used to a function returning some kind of vector or list or data from some kind of data, some kind of objects, all right? A couple of interesting things now. Well, one interesting thing. What does interaction term return, right? Well, what does it claim to be doing? Interaction term says, I'm taking this construct called reputation, REP, taking a construct called INV, and I'm going to create an orthogonalized interaction term for you, all right? If that's the case, then if that's the case, then what should it return? Ideally, what it should return is some orthogonalized data, right? But how could it possibly do that? I haven't given it any data. There's no data provided to this interaction term variable. There's no data provided to this constructs. So what is it doing exactly? All right. Let's just run it and see what it returns. Whoa, what's this? That's interesting. When I just run interaction term, what it returns appears to be a function. Interaction term is actually, and if you look at the class type down here, interaction term is returning a function. That's kind of weird. A function that returns a function? That's what's inception. What's going on here? Why would a function return a function? All right. And that's the question for my next topic, which is why does interaction term return a function? And why would a function in general return a function? That just makes no sense. It is a function. Shouldn't you be doing something and returning to me some results? Why are you returning a function? All right. So to answer this question, I want to kind of introduce you to a concept in programming, and it's sometimes called currying or functional currying. And I'm so sorry to disappoint you. When we say currying, we're not talking about food. We're not talking about like gali, okay? We're actually talking about a mathematician whose last name is Curry. Okay, so don't get too excited. By the way, I hope you had dinner. If not, maybe you're getting hungry just talking about this. All right, so let me do a little demonstration to show you why sometimes you want a function to return a function. All right, so here's my little demonstration. And this is a silly demonstration, but let me just play with it in any case. All right, so let's take this example. I am going to, all right, I am going to create some data here. So my X data is either some data frame. It's some values of X1 and X2, okay? And they're both random numbers, okay? So imagine I've got this variable, this my X data, and it's a data frame of X1 and X2. And I'm doing a very long analysis, all right? I'm not going to show you my full analysis. I'll just tell you I write a lot of code, and later on somewhere, I want to use my X data. And here's how I want to use it. I have a variable called y1, all right, and it's some random numbers. And I'm going to run a regression of y1 regressed over x1 and x2, and x1 and x2 are actually coming from my X data, all right? And that returns to me these results. Now I do some more analysis, and then later on I have to do something else with my X data. In this case, I have a y2 variable, and I want to run this same model again, but this time with y2 instead of y1. All right. You'll notice here in this code that I've essentially had to repeat myself and rewrite this model 2 times with a different y variable, but with the same predictors and the same data. Okay. So I'm essentially having to kind of keep track of this my X data, this X1, X2, copy and paste this model wherever I need to use it. Well, what's the problem? The problem is simply that if I ever change this model, X1, X2, I have to go, the predictors, I have to go find all the instances in my analysis where I was using X1 plus X2, and I've got to go change it, okay? Or if I, all right, so this can be a little bit unsatisfying that I've got to like repeat this code again and again, with the possibility that, let's say, maybe my predictors might change in future and I've got to go change all my code again. Is there some way to write this more elegantly and not repeat myself in my code? Well, let's take a look. All right, so I'm unhappy because I'm unhappy because I have to pass my predictors and repeat my model every time I need to use it. Okay, let's take a look at a different solution to writing this code. Here's my solution. I'm going to make a function, right? I'm going to make a function that takes some data. Here's the body of the function. Here's the code of the function. And what the function does is, whoa, the function creates a function. This function creates a new function with no name, which takes a y variable, and it regresses y over all the data in dot means all over all the other data. And the data I'm providing it is the x data from here. So when I hit enter, I've got a function called y regression, and it returns to me, and y regression is a function that returns for me a function that takes y, and that function runs a regression with y regressed over all the data in a data set. Okay, how can this possibly be useful? What the hell's going on here? Well, take a look. Now, I'm going to run this y regression function. Okay, so y regression, remember, is a function that takes some x data. So I'm going to run y regression on my x data. What is it going to return? Well, whatever it returns is called lm with x, and lm with x, oops, excuse me here, lm with x, oh, look at that. This is the smaller function that was within y regression. So when I ran y regression and provided in my x data, it is now returning to me a function, a new function, which just needs a y variable. And given a y variable, it will run a regression of y regressed over all the data I had earlier provided it. So I called y regression with my x data. So what I now have is a function that is ready to run a regression with my x data. All I need is to provide it a y. All right. So lm with x is a function that is going to run for me a regression. And let me show that to you. If I now run lm with x and give it y1, bang, it runs that regression for me. If I run lm with x and I provided y2, bang, it runs that regression for me. Okay. So essentially what I did here was, since I've got some behavior I need to run again and again, and each time I'm just going to change one little thing in it, I can use this trick that we sometimes call currying. Okay, and what currying really does is that we create a function that is basically a behavior that we promise to run for you later when you provide me all the information. Okay, so what we're doing is we're creating a function with partial information, and we go ahead and create a new function that executes what we want to do eventually with the partial information. But since we cannot run this lm right now until we have a y, I'll just return a function that expects a y. Okay, and then whenever we have the y, and so then when I run y regression, I get a function called lm with x which is going to run my final analysis. It just needs one more bit of information, like y. And so in this case, when I pass in y1, it now runs the function within lm with x with the y1. It remembers my x data because I provided my x data to y regression, which used that to set up this function. All right. So currying is it sounds like an advanced technique, but it's actually a pretty helpful technique when you have some analysis you want to run again and again and again, and you only have part of the information right now. You don't have the full information right now. So what you can do is, since you cannot run the full analysis right now, you set up a function which is set up with all the information you have right now. So y regression is set up with x data because that's all we have right now. And instead of performing the regression, it returns to you a function that will later perform that when you provide me the final bit of information called y. All right? So this is called currying. You make a function that needs one more bit of information to finish your analysis. Okay? And that is actually what's going on. If I can go back to my seminar example, that's what's going on with this interaction. All right? When I define this interaction, I would like to go ahead and create an interaction term between REP and INV and orthogonalize it, take the product, regress the product over these original terms, take the residual, etc., etc. But I can't do that because I don't have the data yet. So what this interaction term does instead then is it kind of does all that without the data. And it says, okay, please provide me the data and a few other things, and I will finish up this creating this interaction term for you later when all that information is available to me. It's just not available to me right now. Okay? And it's only when I create the structural model, load the data, and then run estimate PLS. Within this estimate PLS, the code for estimate PLS, and I can run estimate PLS actually. Well, not run, I can show you the code for estimate PLS. So this is the code for estimate PLS, and somewhere in here, I will process the interactions that you have given me. Okay. So this is an example of, so what you, if any of you were like running my code and having a look at it and thinking, what's going on? How come, for example, even this SECMM object, this measurement model, if any of you took a look at it, you may have found what's going on. It's a list of, looks like some vectors of, some vectors, and in the middle, suddenly there's a function. What the hell is this function doing in here? All right. And that's what's happening. We're actually saying we have some more analysis to do later. We won't do it right now. We will simply do it when we have the full information available to us. All right. Okay, so this was a little bit of advanced. Well, I don't want to say it's too advanced. It's a helpful thing that we want to do. Now, are you going to use this when you're analyzing data? Rarely, rarely. However, what my students who worked on seminar and I found out is that this is often a really helpful thing to be able to do when you are writing code not to analyze data, but when you're writing code that you want to give to other people to help them run some analysis, all right? So there will be times where you want things from them, but you cannot do everything because you don't have the full information. And you can use a trick like currying, all right? So this is an advanced topic. So if you feel like, I'm not entirely comfortable with it, feel free to just play with the example, like this example of, on this slide, function currying that are provided to see if it makes more sense. Any questions on this? I'm going to fill up some water for myself to see if there's anybody with any questions. Anybody? Okay, great. There's another, well, I wouldn't say advanced, another interesting feature within Seminar that maybe you've picked up on. So remember this line on interaction terms? where I provided it a word like rep, R-E-P. I provided the name of the other construct, INV. And then I say the method is orthogonal. But orthogonal, I didn't write, I didn't say orthogonal in quotation marks. I wrote orthogonal without quotation marks. What the hell is this thing? Orthogonal is a function. This is actually the function that does the orthogonalization, all right? And this is another kind of interesting use of a function. Here, when I ask you what is the method you want to use to create this interaction term, I'm actually saying what is the function you want me to use to take these two constructs when I have the data and do something with them. What is the function you want me to use? And orthogonal happens to be a function we wrote within the seminar package. And so you just have to pass the function to us, okay? And the reason we did it this way, I mean, we could have just said, pass me the string orthogonal, and then we say, oh, if the method is orthogonal, then use the orthogonal function. Why did we have you pass in a function directly to us rather than the name of the method? And the reason we did this is because it's possible now for you, the user of the seminar package, imagine that you want to create a new way of creating an interaction term, not, orthogonalization. Let's imagine there's a new technique out, right? All you have to do is create your own function and pass it into the method. It doesn't have, I mean, method is not expecting a function that's written by the seminar authors. It could be written by anybody. So you could actually write your own method for creating interactions between items, and you could pass that on to seminar, and we could use that, right? So, so this is another interesting use of functions where you can provide functions to functions so that, later on, whoever is using your package or the code you're writing can replace this with a function that they themselves wrote, okay? This really extends the utility of this library by allowing other people to inject their own behaviors into it, okay? So that way we don't have to say, oh, the techniques that you can use to create interaction terms are all hard-coded. You cannot change them. It's orthogonalization, repeated indicators, et cetera, et cetera. No, now when someone says, hey, there's a new technique, when will you implement it? We'll say, well, you can implement it. You can make a function and you can just put it in here and we will use your function instead of our function. So these are some advanced ways of using functions. And I just thought it'll be kind of good for you to kind of see how these are done and how they're used, okay? I'm looking at the chat window. Thank you, Guild, for your vote of confidence. It's either too cool or too nerdy, depends on who you are, right? All right, cool. So this is some advanced use of functions, and I thought I'd just kind of expose that to you because we're in a class on computational stats. So just to kind of emphasize the computational part of it, okay? And it's certainly possible that when you use other libraries, packages, whatever, that you will come across something like this, and then you won't be surprised, like, what's going on? There's weird use of functions in here. This is what's going on, okay? Cool. All right. That's all I wanted to mention about functions. Let's move on to the next topic or thing, all right? So I am going to move a little, I'm just going to move one by one through everything I want to discuss today. All the stuff I didn't have time during the semester to talk about, okay? Okay, let's take a look at some code. Here is some code that I wrote, okay? What does it do? It reads in a CSV file. Then it takes a subset of that file that I read in and only looks at people at age below 40 in that data set that I read in from the file. So I'm going to call them SEC young. To me, young is less than 40. Okay. Sorry, anybody over 40. Me too. We're not young anymore. All right. And then what do? Then with this subset data set, I compute these two variables divided by each other from this data set. All right. And I call that security, wealth, age. And then the final result is I just want the first 5 elements of this computation. So if I kind of go run it here, it's 1, 2, 3, 4. This style of coding, we just call this a procedural style of coding. All right, this is sometimes called a procedural style of coding. And the reason is because we're following a procedure. We're doing step 1, step 2, step 3, step 4. And what you can see here is for every step, I'm kind of giving a name to the step. I'm storing the result of that step in a variable. And so that variable is kind of the name of that step. Okay, so I had to do 1, 2, 3, 4 steps, and then I get my results. All right. Sometimes when these steps are very obvious, you may not. Okay, so that's one example. I'm sorry. I'm not going to get too much further into this. Okay. So, and by the way, here's the result. The result is this. Okay. Let me show you another example. Okay. Here's another example, a different example. So in this example, I've got a vector, dogs, cats, rats. Okay. And I'm using this function called grepl. And what grepl does is it just checks whether this string at exists in any of the words in this vector. So is there the letters at in dogs, cats, or rats? As you can see, it's in cats and rats, but not in dogs. When I run this, it tells me false, true, true. It tells me at is not in dogs, so false. It is in cats, it is in rats, so true, true. All right, great. So what's wrong with this code that I wrote here? The truth is there's nothing wrong with it, okay? But it's possible that for some people this code is a little hard to read for a couple of reasons. First, it may not be, like, let's take this first chunk of code. It may not be obvious looking at that chunk of code that actually I am not interested in all these things that I'm doing. All I want is this result over here. All right, so I've got 4 steps, but the reason I did this, and this, and this is really to do this and come up with the results. So sometimes when you're looking at code, you see like a lot of lines together, and you don't really realize that these 4 lines belong together. They're trying to all collectively do one thing. All right, so that could be a stylistic problem with this code. It's kind of hard to see, like, that this is a single thing that I'm trying to do with 4 steps. What's wrong with this line of code? Again, I don't think there's anything particularly wrong with it, but some people may feel that this is a little hard to read because, I'm trying to search for this word in this vector, so I think this is quite readable. But maybe somebody will say, well, it would be more readable if you told me, look, I have a vector, and from that vector, I would like to search which words have this pattern in it. So somebody might complain this is in the wrong order, right? Like maybe this should be written first, and then this should be written second. Okay? A little bit like, when you multiply 2 numbers together, you don't say times 5 comma 2. You could. This is called reverse Polish notation. This is, maybe in some languages, this is the way you multiply numbers together, actually. But, in R, you say 5 times 2. You say, okay, give me one of the numbers, then tell me what you want to do with it, and then tell me the other number you want to use to do that thing. All right. So in that similar way, somebody may say, listen, you should have really told me about this vector first, and then told me that given this vector, you are trying to search it for this pattern. Okay. So maybe to some people, this is hard to read because the order is not how they're expecting it. It's not in the left to right order they are expecting it. Okay, this is saying search for this within this vector, but maybe some people are expecting, given this vector, search for this. All right. So it's possible that when you're writing code which has multiple steps, in this case I have 2 steps. One is to define this vector, one is to kind of run this grep search function, that the steps are not in the order that the reader expects, maybe. Okay. So what can we do about it? In class, I mentioned one solution, to this kind of potential problem. And that was to use piping. This is a new feature of R. It may not be in your R because it only came out, I think, in April. So if you haven't reinstalled R, you may want to reinstall it because this feature is now built into R. Okay. And so here's a new technique called piping. And let's take a look at what piping looks like. Okay. So with piping, this earlier example I had here. Oh, by the way, I forgot to put this into my code. I'm just going to put it right here. Okay. So let's take a look at this example I had. There's like 4 steps to compute this result. With piping, we can run it like this. Okay. And what this says is step number 1, read this file from disk. Step number 2, subset it so that we only want the data from this file, which is age less than 40. Step number 3, okay, with that subset, just compute this. Step number 4, just return to me the first 5 results. Okay, this is called piping, and this gives me the same result as before. All right, and you'll notice something special about piping, which is that every time I call one of these functions, like let's say subset, I didn't tell it what I want to subset, I just told it how to subset it. Similarly with width, do the following calculation with, I just told it the calculation I want to do. With head, I didn't tell it which variable I want to get the first 5, pieces of information for. I just told it 5. So implicit, when you use piping, every function implicit in it is that the first parameter is the result of the last thing I ran. Okay, and this is called piping. It's a really popular feature nowadays, especially in the last 5 years. And almost all the languages that I use or know of have introduced this as a native feature in the language. It's almost too popular. I'm a fan of piping, but sometimes people take it a little too far. For example, some people will say, "Oh, we can write this even more piped." So somebody will say, "Let's take the name of this file and let's pipe that." So we take the name of the file, we pipe it to read CSV, pipe it to sure, that works, and that gives me the same results. Okay. But I think we've gone one step too far. I don't really need to start with the name of a file. That's just a little too crazy for me. So to me, something like this is perhaps what I need. Just tell me the 4 steps. So piping is really nice. Piping is one solution. It gives you like it tells you the things you want to do in step by step. Okay. And when you look at this code, you don't have to worry about what each one is doing, and you don't have to worry about all these extra variables they're creating. You can look at this code and you can know that, oh, I'm trying to get the result of these 4 steps. If you're not interested in what those 4 steps are, you don't even have to read them, just get the results. Okay, so to some people, this is more readable. All right. Quick poll. How many of you think this block of code is more readable than using pipes? It's subjective. I will not say you're right or wrong. Anybody? Anybody? All right. Just to make sure you're all awake and looking at me. How many of you think this style of code is more readable? Use the raise hands feature. Okay, we're getting some votes in now. Fantastic, great, thank you. All right, so several of you actually feel that this is more readable. Great, thank you. All right, okay. All right. Okay, so you agree piping is helpful, okay? However, piping doesn't work, native piping doesn't work everywhere. Let's take this example here. How could we write that piped? Because I said maybe some people want the array to come, the vector to come first. So I make the vector and then I pipe it. Oops, But now the problem is I need to take this result, and I don't want it to be the first parameter. I need it to be the second parameter of grep, because grep is expecting the data that you're searching to be the second parameter, not the first parameter. Okay. Unfortunately, this doesn't work. Okay. There's nothing you can kind of like do here. It'll complain to you. All right. So native piping doesn't work if one of the functions is expecting it to be the second or later parameter, unfortunately. Okay. Um, there is a solution around this, but it's not an elegant solution. What was the solution? I can't even remember. There's a couple of solutions around it, but I'm not going to get into it because they're not elegant. Okay. So this is a limitation with like native piping. All right, is that if the last object, if it's not going to be the first parameter of the next function, it doesn't work. All right. There's a couple of solutions to it though, and let me show you what those solutions are. And the first solution doesn't require any special library. It looks like this. This is called forward assignment. I'm not sure I've shown you this in this semester. Have I shown you this style? Just raise your hand if I've shown you this style this semester before. No? Nobody? Okay. So this is a style called forward assignment. In forward assignment, essentially what I'm doing is I'm running each line of code, and you have all seen like this before, right? You've seen assignment going right to left before. Well, guess what? In R, you can also move the assignment the other way. Oh, excuse me. You can also move the assignment the other way around. You can assign left to right as well. Just reverse the sign of the arrow. Okay? And we can use that trick like this. I'm going to read this file and I'm going to store it in a variable called dot. Dot is actually a valid variable name in R. You can have a variable called dot, no problem. And then the next step, I'm going to take the dot from the previous line, run subset on it, and save it back in dot. Okay. So this is an interesting kind of style of code. And when I'm done with it, I'm going to put the results in results. All right. So altogether, it looks something like this. And here's my result. Ta-da, it's the same result as before. So this is another style of doing this kind of sequential procedural coding using what's called forward assignment. All right. So instead of saving it to a variable each time, you save it forward to some temporary object. All right. Okay. All right. I see a couple of questions, and I'll try to address them in a moment. So I see a couple of questions in the chat window. Give me a little bit before I get to those questions. Okay. So this is called forward assignments. All right. And actually, we can use forward assignment on this example. We can, create this vector, assign it to dot, and then run the grep on dot. It works just fine. Okay. So forward assignment is interesting. And it has an advantage, and it has advantages and disadvantages. The disadvantage, obviously, is it can be a little painful to always have to type forward assign dot, forward assign dot, forward assign dot. It can be annoying, okay? No doubt. All right. So that's a disadvantage. There is, however, a couple of advantages. One advantage is, we can do stuff like this. If we store the result of a line in dot, we can use the dot wherever we want in the next command. So that's great. All right. There's one more advantage of forward assignment that people often don't mention. Okay. By the way, excuse me that RStudio keeps telling me unexpected token, unexpected. This is such a native piping is such a new feature in RStudio that RStudio doesn't even know what the hell this is yet. I believe over the past weekend there was a new version of RStudio. If you reinstall RStudio, I think it'll know what it is, but I haven't reinstalled it. Okay. There's one more thing about forward assignment that has an advantage I want to quickly mention. So with this native piping, notice that I cannot run just one line or two lines at a time. When I hit like, you know, Command Enter or on a Windows Control Enter, it runs all 5 lines at once. You cannot like run one line and see, hey, what's the answer? It's very hard to debug it. To debug this, I would literally have to like change, stop piping it and, do something else because I cannot just run one line at a time. With forward assignment, actually, you can run one line at a time. And at any point, you can stop and ask, what is dot so far? Okay, so that's kind of nice. You can debug quite easily, all right? And then you can continue until the results. So this is a nice feature about forward assignment that you can debug it by running it line by line. Okay. So with that said, there is one more option, and I think a lot of you know this last option because I see it on some of your homework assignments. All right. The last option, and probably the most popular one, okay, is to use this library called Migrator. You'd have to install it. You'd have to say install packages Migrator. But once you've installed it, all you have to do is just, load the library. Okay. And here's how the Migrator function looks like. Here's the code for it. Let me just run it. It looks almost exactly like native piping. And actually, this Migrator library was written long time ago, no, not long, but quite a while ago, before there was native piping in R. So it does piping the way native piping works. Okay, so it's almost exactly like native piping, except they have this funny symbol. By the way, the folks who wrote RStudio, I think some of them are also involved with Migrator or they use it a lot. So RStudio has this nice feature that if you do on a Windows machine, Command Shift M on Control Shift M, or on a Mac, Command Shift M, it'll do that Migrator pipe for you. Oh, that's kind of cool. All right. So if I say 5, Command Shift M, X, that works. Oh, no, it didn't work. Doesn't matter why, but okay. So this is the Migrator library, okay? And it looks like it does native piping. So is it the same as native piping? No, it's got a couple of extra features. One extra feature it has is the pipe from the Migrator library. It can actually put the result of the previous operation in the second position of the next function. All you've got to do is put a dot where you want the results to go. Ta-da! So the Migrator library effectively does something like the native pipes and something like the forward piping together. All right. So there was a question on the chat window. Someone asked me, hey, what's the difference between the native piping symbol and this symbol? Well, this symbol is not native to R. This comes from the Migrator library. This symbol is now, as of April 2021, native to R. Okay. And the Migrator library is heavily used in data science. So I strongly suggest for those of you who are interested in data science, be familiar with this library. Okay. And this library does a lot more than just this. If you go to if you just search for Migrator and you find it online, it has a lot of different operators. This is one of the operators it provides. It's got some other interesting operators that you can look at. You can kind of go play with, okay? I'm trying to see some examples over here. One example that I really like is this one. This operator runs what's on the left-hand side. It passes as the first parameter the previous result to the right-hand side. All right, so whatever this returns becomes the first parameter to square root, and the result of square root is returned to the left-hand side and it's set back to whatever this is. So it moves data left to right and then moves it back to the left and assigns it back to the left. Okay, so it's a pretty interesting operator. All right. So it's got so there's a whole bunch of really interesting stuff in MagRitter. So welcome to take a look at it and play with it. All right. So I do recommend for those of you who are really interested in more data science stuff to play with this. Okay. All right. Let me look at some of the questions that are in the chat window. So Guild, I hope I have answered your question. I think the MagRitter is a more powerful. It can also do this little dot thing. All right. However, there is one situation where you may prefer native piping over the MagRitter library, and that is native piping is faster, all right, because it's built into the language, all right? So native piping is a lot faster. In fact, what native piping does is the following. So when I wrote my native pipe code like this, right? Oh, by the way, result, right? Oops, excuse me. This is not native piping. So the native piping look like this, right? It's really, really fast because what R does behind the scenes without telling you is it does this. It, one second. It takes this code and basically it converts it into this. Okay. It converts it into no, don't tell me I lost it. Damn it. I lost it. Okay, so let me do it here. So native piping is super fast because what it essentially does is oops, it basically does something like this. That's exactly what it does. It puts them all one within each other onto the same into the same function call. Okay, this would be impossible for you to read, but this is exactly what native piping does. So writing this code, it's exactly the same in R as writing this code. So it's very fast. It doesn't have to create any intermediary objects and stuff like that. Okay, native piping is going to be faster than forward assignment, and it's going to be faster than MagRitter, okay? But that should not be a concern to you unless you are writing your own package for somebody else to use, or you're working on some problem that's extremely computationally heavy, okay? Okay. All right. There was another question here. Is if there is more than one argument in the function, is it suitable to use piping? Native piping, I would not use native piping if you have to pass some object, some results to the second or third or fourth parameter of the next function. If you really want to do that, use MagRitter. It'll do that for you. Okay, so that's my answer to that question. Great. Oh, hold on a second. Chat. All right. Okay. Any questions? Otherwise, I'll keep moving forward. Any questions so far? All right. So let me continue ahead. So this was my basic demonstration of like what I call forward moving code. It's sometimes called eastward moving code. It's moving left to right, okay? So that you don't have to like read things right to left, or you don't have to read things, you don't have to interpret multiple lines and figure out what's going on. All right. Okay, moving on to the next thing so we can get done early. The next thing is I'm just going to mention very quickly. This semester, we saw this manipulate function. And we use that in a couple of places. We use that for this tutorial on distributions and how you ran this little tutorial. Um, uh, and um, for those of you who don't remember this, go back and look at when we talked about error and power. We saw this manipulate function, which allows you to basically create a visualization and then tell R to update the visualization whenever some parameters change. And you can create, for example, here, some slider bars that people can change, and it'll keep rerunning your function that creates your visualization for you. Okay, so that was a manipulate function. And I just wanted to mention, for those of you who found that really interesting, that there's something kind of similar to it called Shiny. All right, you can go Google Shiny in R, and there's a feature that the makers of R Studio have made, where you can do something like manipulate, and you can actually deploy it on the web. So you can actually write some code, and what's on the left hand side can be like put on a website, and now people can interact with your graphics in real time over a browser. All right. So if you're ever interested in creating interactive visualizations in R, go have a look at this Shiny package. All right. It will help you kind of create interactive things. The code is a little bit more complicated than manipulate, but it's not that hard. You can see here, for example, that we're creating a page where with an input with like 1, 2, 3, 4 inputs. One of the inputs is a checkbox, one is a date range, one is a selection, one, et cetera, et cetera. So the code is not too hard, and you can really create these really nice interactive visualizations that you can deploy on the web. All right. So you're welcome to go take a look at that. Go Google Shiny or go to shiny.rstudio.com to learn more about that. All right. So that's just one thing I wanted to quickly mention that I didn't have time maybe to mention during the semester. Okay. All right. Moving on. Sorry, today's just a bag of things I never had time over the semester to tell you. The next thing is about coding style. So this semester, I've focused on very low-level coding style, and it may not look, it in fact will not look like the coding style of many professional data scientists. But what I've shown you this semester is all the low-level stuff about R that you need to know. My strong suggestion for those of you who are interested in data science is to go to this resource called R for Data Science. All right, I've got it open right here. And R for Data Science is basically, and you can just start from the top and read to the bottom, and it'll introduce you to like a more professional way to write your code. All right. For example, it will introduce to you like it'll introduce to you the ggplot2 library, which I notice a lot of you are already using. How many of you were already using ggplot or ggplot2 to do your assignments this semester? Can I see a show of hands of the people who are here today? All right, we have several people here who were already using ggplot2, so that's awesome. Great, thank you. All right. Um, all right. So a lot of you are familiar with it, and that's just for like visualization. So this helps create really nice visualizations with very friendly code. Okay. Um, there's no downsides to using ggplot2. The only downside, well, maybe there's one downside, which is probably you'll be always Googling how to do everything because it's not always obvious how things are supposed to be done. But there's so many resources out there on how to use ggplot2 that whatever you're trying to do, just Google for it and you'll find a solution. So you can create really nice visualizations using ggplot2, and it's really easy to use. All right. But that's just data visualization. This website, R for Data Science, will introduce you to a lot of other things about coding, and so on and so forth. So it's got a lot of other things, how to do transformations really well. It'll introduce you to, instead of using data frames, they will really encourage you to use something called tables and things like that, okay? And you'll find that your code will be much easier to read by other people and maybe also easier to write, okay? However, and all these, and basically in most of these chapters, it'll introduce you to different libraries, which ggplot2 for very good visualization. For workflow, I think it will, or data transformation, it'll introduce you to tidyverse, okay? So, or dplyr or something like that. So it'll introduce you to a whole bunch of packages, which are collectively sometimes called the tidyverse. It's like the universe of tidy packages that'll make your code really look tidy and neat and clean, okay? And you may wonder, well, if this is so nice, how come you didn't teach this to us in class? Well, two reasons. One reason is it's so easy to learn, you don't need a professor to teach this to you. This website does an amazing job of teaching all those tools to you. So for those of you who are really interested in getting into a more data science career and perhaps using R to do so, go read this R for Data Science. I think you can also get it as a book, but it's also available here as a website. Okay, and the website is free. The book you'll have to probably purchase on Amazon or wherever. Okay, so I encourage you. So one reason I didn't teach in this semester is it's super easy to learn. As you saw, a lot of students in the class were already using many parts of this, and I didn't have to teach them how to use it because these tutorials are so easy to use. But there's a second reason why I didn't show it to you, because I wanted to make sure you really understand the core R language itself first. Because a lot of classes on data science, they just teach tidyverse stuff, but students coming out of the class cannot do basic stuff in R because they've never seen it, okay? So I spent this whole semester showing you all the low-level basic stuff in R, but please take time and learn R for data science. It'll teach you a whole bunch of packages that'll make your code look a lot more professional and neat and tidy, okay? And it's super easy to learn. I've never heard of anybody who say, oh, I couldn't learn it through this book. It's just so easy and easy to read and use, okay? Okay, so that's my suggestion. It'll teach you ggplot for visualization. It'll teach you the dplyr, dplyr, I think that's what it's called, dplyr package for data transformation. It'll teach you tibbles, magrittr pipes, R markdown, and other things for wrangling, programming, and reporting and stuff like that, okay? So it is, if you are going to be writing data analytics code professionally, where your job is to analyze data, it would be crazy not to use these tidyverse packages. So you should absolutely go and learn it. Great summer project for yourselves, okay? And it's super easy to learn. You will not find any difficulty. Is there a downside to using these packages? Not really. I can think of one downside, which is it may not be a lot of these packages are not very performance oriented. They're not supposed to be fast. They're just supposed to be very easy to, the code is supposed to be easy to read, but it's probably going to be slower, a little bit slower. It probably doesn't affect you unless you're doing some kind of analysis that needs to be run in real time and has to be conducted all throughout the day, and it needs to be really, really fast for some reason. If it doesn't need to be fast, then don't worry about it. Use the tidyverse. It's excellent, okay? Um, the other the other situation where I think it's maybe where I would avoid using these, helpful packages is when you are yourself writing a package for other people to use. Because when you're writing a package, I think it's a really good habit not to require too many libraries, because it sucks to install a package and see it's installing like 30 other packages, and each of those packages is installing 30 more packages. It becomes crazy, okay? It installs a lot of dependencies, and if one of those packages breaks, it breaks everything. So if you yourself are writing a package, my suggestion is try to avoid any deep dependencies. Try to write just using the base R libraries as much as possible. Okay. But I think for the vast majority of you, if you're interested in data science, you'll be probably doing analyzing data rather than writing production code or writing packages for other people. I write packages for other people, and I write production code. So I am worried about these things, but I don't think most of you should be worried about it. So by all means, go ahead and learn these tools. They're fantastic. Again, like I said, a great summer project. You can probably knock it out in 2 to 3 weeks easily. All right, great. Any questions on R for data science and the tidyverse universe of packages like ggplot, dplyr, tibbles, magrittr, all this stuff? Any questions about any of this stuff? Not technical questions, but like any high-level questions from anybody? No? Okay. Okay. All right. There's a third reason I don't teach you this stuff in my class, because it would take a lot of time in class, and I'd rather teach you basic computational stuff. Okay, all right. Speaking of basic computational stuff, let's get back to like hardcore computation. I talked about the data table package earlier this semester. Do you remember? Like we used data table to load that huge data set for the recommendation systems. Like when I gave you that Picolage data set, we used data table to like, load it up. And for those of you who are going into directions where you're writing high performance code, again, not everybody, right? But if any of you are writing code and you're going to be dealing with a lot of data of very heavy computation, you need it to be faster. You really need it to be faster. Data table might be your friend. Okay. So go ahead and read more about data table. It's not the friendliest package to use, but it is a high performance package. Okay. And if you compare data table to like base R functions that do the same thing, like this is literally a plot showing you some different packages like read R and like some base R operations. Data table's down here. Data table's like blisteringly fast, okay? The reason data table is so fast is because it behaves like a data frame, but it changes your data. So, like in data table, if you change a column, it literally changes your data, whereas data frame would make a copy of all your data. So it violates the spirit of R, which is to always make a copy of data when you're going to modify it. Data table changes stuff in the table in real time, but it does so with an eye for performance. All right. So for those of you interested in data tables, certainly use it. Here is again, some examples of data table. This is data table down here. Well, there's two different kinds of implementation of data table. Trying to do a subsetting operation. So it's trying to find a part of the data based on a condition. And if you use like the subset function in base R, the bigger your data size is, the more time it will take. It'll take a long time. Okay, not quite linear, but it takes a long time. The dplyr library that comes as part of the tidyverse that I was explaining before is faster than base R, but it's still quite slow. Data table is really fast. It's like the fastest library in R for high performance computing. Okay, so again, those of you using who need high performance computing for some reason, explore data table. It's not the friendliest thing, but it's fast, and it's not just fast for R because R is a slow language. It's fast. A lot of things in using data table are faster than a lot of other tools in data science. It's faster. A lot of operations in data table are faster than using Spark or using like Python libraries. Is faster than dplyr and other things. Um, and in fact, if you have a very large data set, a lot of libraries in R and other languages will just die. They will just report an error and say cannot handle so much data. But data table can handle a lot of data and it's super fast. Too bad it's really hard to write. It's a little bit hard to learn to write and write code with data table. Um, by the way, data table has become so famous that in the Python universe, they have a library called PyDataTable. It's basically do I have a copy of it? Do I have a version of it here? So PyDataTable is actually a version of data table in R, but written for Python. And it actually kind of like tries to copy the idea of data table, but it's still not as fast as data table. Data table is ridiculously fast. Okay. So for those of you, again, last time I'll say it, who are for some reason doing some computation and speed is of the essence, you cannot wait to get the results. It's something you need to be doing maybe every minute, and it's a big task. You need to run it every minute, or maybe you have some analysis and it will take you days, and you need to run it in hours instead. Maybe data table is your friend. Okay, so I just want to put that in your ear. It's a high performance library that comes that you have to install for R, but and it's not the easiest thing to use, but it's apparently quite powerful. Okay, great. And that's all I will say about data table. But I just again another tool I want to put in your belt for some of you. All right, all right. Let's try to. Okay, I got a couple more things. I've got a few more things to discuss, and then we'll finish up. Okay. Something more about high performance. So we talked earlier about where is it? Where is it? Where is it? Sparse. Okay. We talked about sparse matrices before. That's a matrix which has which is mostly zeros. Okay. So for example, here I'm creating a matrix called M1. M1 is 2000 rows and 2000 columns. So basically M1, you know, is 2000 by 2000, so it's 2000, squared. It's oh well, that doesn't help me. It's like 4 million values big, right? However, it's mostly zeros. So when I set up M1, it's a matrix that's mostly zeros. And I've just assigned 100 random values to be one. So out of 4 million, a space of 4 million, there's only 100 actual values that are non-zero. It's a sparse data set. And we saw sparse data sets when we did this cosine similarity problem. And back then I told you about some library that can do cosine really fast on sparse libraries, okay? There is another library, and I don't remember if I mentioned to you, it's called Matrix with a capital M. And this matrix library is really interesting because with the matrix library, you can create a matrix with the same, it's almost the same code as like what we had before, except with a small m, you use a big M. And with the matrix library, you can tell matrix, this is a sparse matrix. Use some intelligent tricks, okay? Um, so that so M1 now is a regular matrix. All right, and M2 is, and they're both, and M2 is a special matrix made using the matrix library. What's so different about them? Because I told the matrix library that M2 is a sparse library, it's done a couple of interesting things. First of all, let's look at the regular matrix and see how big it is in memory. M1, the library M1 created the traditional using base R matrix is, ooh, how big is this? It's about 32 megabytes it's taking about 32 megabytes of memory. Why is it taking 32 megabytes? Because every number in it is taking, well, this should be exactly, is taking about 8 bytes, okay? So it's 32, so let me just kind of repeat, this is 32 megabytes in size. How big is the M2? The matrix library has intelligently told itself, I don't need to store the number 0 using 8 bytes every single time. So it's able to store the M2 matrix in a lot smaller space. How much smaller? This is about 300 times smaller. Oh, excuse me. M2. Okay, it's about 240 times smaller. So first of all, using the matrix library, if you have a sparse matrix, it takes a lot less memory on your computer in case you need that memory for other things, okay? What else? If you try to do a big computation on a sparse matrix, it is going to be slow. How slow? I don't know, but I'm gonna pour myself a little drink while we're waiting, all right? It's doing, I don't know, about 4 million operations here. But it's doing it over a matrix and trying to reassemble a big matrix. It's a big mess. And it shouldn't have to be so slow because M1 is mostly zeros. I'm multiplying two matrices by each other. Most of the answers are going to be 0. So I'm totally wasting time multiplying zeros by other numbers when I do this operation, okay? And as you can see, it is actually quite slow. It takes about 35 seconds to run. What if I did the same thing, but I use my sparse matrix from the matrix library? Oop, it's done. That's so you can see the difference in time. It's like, I don't know, almost like 10,000 times faster to use the matrix library if you have a sparse matrix. So for those of you who are doing matrix operations and doing very low level kind of statistical computation, be familiar with the matrix library. It might be your best friend. Unless you want your analysis to be slow so you can go eat lunch, in which case, don't use it. Okay. All right. If you want to tell your boss, sorry, I got to take the day off. The computer is really slow. Okay. So, but anyway, if you're dealing with sparse matrices, learn the matrix, learn about the matrix library. Couple more things. Parallel processing. Now, um, on most computers, um, the chip on your computer that is doing all your computation has many heads with which it can think. We call these heads cores. Okay, so the processor on the chip, the big, it's more than a chip nowadays. It's like a system on a chip. So, but let's call it a chip. Like your CPU actually has multiple cores, which means it can actually compute. Let's say this is a 4-core CPU. It can do 4 computations at the same time. Okay. However, when we are running our code in R, we are running all of it typically on a single core. Okay. My computer is a 8-core. It's not even 4-core. My computer is an 8-core. There are computers out there that are up to 32 cores. Okay. But all the code we've seen this semester, and let me see parallel. Oh, this is going to be slow. I regret having to run this. Okay. So for example, here's a bootstrap function which runs a linear regression. And I'm going to run it. Oh, crap. I shouldn't do it 6,000 times because it'll run forever. Okay. I'll let it run. It's going to take a long time. And what's happening now, and I would like to show you all my cores. However, this is actually an image of all my cores right now. And originally what I wanted to show you is that one of the cores is doing all the work. I can't show that to you because I am using Zoom, Google Meet, and I'm live streaming on YouTube at the same time. My computer is dying. Okay, so I can't really show you that one of the CPUs is doing all the work, unfortunately, because they're all so freaking busy right now. I did a dry run of this before today's class, and like all of these were 0, and I was like, yeah, it's so easy to see, but you can't see it here, unfortunately. Um, but okay, God, that took 30 seconds. Okay. Um, and it takes a long time because I'm running all of this on maybe 1 or 2 cores. Like my computer is not very efficient. I'm not using the real computational power of my computer. And nowadays, all computers, even your mobile phones, have multiple cores. But the code we write is using, unfortunately, only 1 core because that's the way R works. Okay. Um, Right. Yeah, Yenyu has a great suggestion, which is, run this later and take a video on the phone and upload it to Canvas. Sure, Yenyu, I'll do that for you. Okay. Gil says, buy a cutting edge computer. Gil, this is a cutting edge computer. God damn it. It's like only a few years old and it's like 8 cores and it's hyper-threading and it's still slow as hell. Okay, because it's slow right now because I'm running too many things on it. I'm running Zoom, Google Meet, and I'm live streaming on OBS at the same time. So it's really crazy. Not Google Meet. Excuse me. I'm doing Zoom and I'm live streaming on YouTube at the same time. It's just really killing my computer. All right. So what I wanted to tell you though is if you are running code that can be, that doesn't need to be run one after the other. So for example, here, I'm using sapply to run this bootstrapping function 6,000 times. Those 6,000 linear regressions, they don't have to run one after the other the way I'm doing it. They could all run at the same time. They're not dependent on each other. So this is a situation where I could actually run them in parallel. If I have 8 cores, I could run one linear model on 1 core, another on another core, and use all 8 cores if I really, really wanted to. Okay, but that's not what I did. If you do want to run code in parallel, there's a really nice library called Parallel. Okay. Um, and what it allows you to do is to use as many cores of your computer as you wish. First of all, the parallel library comes with this really nice little function called detect cores. And what detect cores does is it tells you how many cores there are on your CPU. And it tells me I've got 8. Okay, so I'm going to store that result in num cores. Then I'm going to tell it, can you make a little computational cluster for me? Like, can you run the code that I'm going to provide you soon on 8 cores? You can set how many you want. I'm gonna make it 8. Okay. And then I've got to create that cluster. And now I can run this same thing. Okay. But now notice, instead of using sapply, I'm using par sapply. This is a special function that comes with the parallel library. It runs sapply in parallel. So if you look on the right hand, if you look at my, it was already busy, but if you look at it now, you can see all my cores are burning. And previously it took, anybody remember how long it took previously to run on a single core? Was it 30, 60 seconds, 30 seconds? Ooh, I can't. If anybody remembers, just write it in the chat window. Yeah, it was like 28 seconds or 30 seconds. It was something like that. Yeah, thank you. 1 minute. Yeah, it was somewhere around that. And now it's finished in 17 seconds. Okay. And if you look at my cores, it was this period right here where all 8 cores were burning at the same time and basically maximized all my cores and said, okay, I'm going to run this computation full throttle right now. Okay. It wasn't 8 times faster because I'm running Zoom and um, live streaming at the same time. So I'm sharing my CPU with a lot of other things. Um, but that's the basic idea. Okay. I'm going to close this now. Oh God, my poor CPU. Um, so that's great. And when I'm done, it is important to tell Parallel, stop this cluster. You don't need to parallelize anymore. We're done with it. Okay. Um, and by the way, if you ran the seminar library assignments for your last homework, when you did bootstrapping, one of the um, one of the parameters you can set is how many cores you want to parallelize over. And if you don't tell us, then by default, we use all the cores. We detect how many cores you have, and we use all of them by default. Okay, so that's a nice handy little thing that my students and I put into seminar is we parallelize across all the cores of your computer by default. Okay, some of you notice that on some Windows machines, R has a little bit of problem. Actually, the parallel library has some problems on some Windows machines. It's fixable, but I haven't fully explored it. So don't lose heart. I think Yenu or maybe some other students, you had some problems. Yeah, running parallel. Don't fret. You just have to Google to see what's going on. There might be some simple thing you can adjust and it'll work, okay? But I haven't explored it fully, all right? So anyway, so that does bootstrapping and so on and so forth. So for those of you who are running analyses which are using replicate or sapply or some apply and it takes a long time, chances are you could parallelize those. So look for the parallel version of your apply function or whatever you're running in the parallel package, and it will immediately parallelize over all your CPU cores. I've got one more thing about parallelization, which is gonna maybe make some of you very happy. Okay, we can parallelize across, let's say 8 cores of my CPU. It might still take 10 hours for my code to run. There's something else you can do with the parallel library. This code that I showed you right here, with almost exactly the same code, you could parallelize your code across multiple machines. Let's say you have you're working in a lab and you've got 20 machines that nobody's using. You could utilize the CPU on all 20 machines in parallel, and you could command them all from your machine using R. And the parallel library will do that for you. How will it do that for you? Go look up the documentation for parallel. And I think I've got a little link right here. Let me see if it shows up here. And actually, the code for it is really easy. The only thing you'll need to do is you will need to know, excuse me, the IP address of each of those machines. If you know the IP address of each of those machines, you can tell it that, you can make a list of machine addresses, tell it like, this machine, this other machine with this IP address, and on each machine, how many cores to use. And the rest of your code is exactly the same. You just kind of like, make a cluster and then run this in parallel. And with very few adjustments, you can distribute your code across multiple machines. So this parallel library is insanely powerful, not only for utilizing all the cores of your machine, you can utilize all the CPUs of all these other machines as well, okay? You may have to set up those other machines in a particular way. I'm not sure how, but go look at the parallel library if you're interested in that, okay? But it's really powerful, and you can run distributed computing across several machines if you wanted to, all right? So I highly recommend for those of you who are running analyses that's taking many, many hours or maybe even days to run, look to parallelize it, at least across the CPU, the cores of your CPU, but potentially over other machines as well. Okay, parallelization, super powerful feature with very little coding, extra coding required. So I'm amazed we can do this so easily. Okay, cool. And there's some links down here to kind of get you started, whichever direction you're going. All right. Jamming asked me, is the parallel concept similar to Bitcoin mining? Hold on a minute. What are you trying to do? Okay, I'm just joking. Bitcoin mining is very computationally intensive. That's the whole purpose of cryptocurrencies, is they're intentionally made to be computationally intensive. And um, a lot of operations like Bitcoin mining are faster when they're done in parallel. Okay, so Bitcoin mining typically, yes, it's run either across all the cores of your CPU. Some people run it on a cluster of machines. So Bitcoin mining is done on a cluster of machines using exactly this kind of technique I'm describing. Okay. More often, though, it's done on a cluster of GPUs because GPUs are custom made for high performance matrix operations. CPUs may not be the most optimal way to run matrix operations. GPUs are often faster at matrix operations. Okay. Which brings me to my next topic, GPU processing. All right. Um, so in R, there's also like so your computer may or may not have a dedicated GPU in it. A GPU is actually a processor with not like 4 or 8 or 16 or 32 cores, but potentially with hundreds of cores. And they're all highly customized to do linear algebra, matrix manipulation, matrix operations, matrix multiplications, stuff like this. Okay? And if you have a GPU, you might be, and you're doing very low level matrix operations. So for example, here, I'm going to create two matrices, just regular base R matrices. Each matrix is about 3,000 by 3,000, so about 6 million cells big. And if I do a matrix multiplication, like A times matrix B, as we saw before, it's going to be slow. This time it's not sparse, so I cannot use a matrix library to make it faster. It probably won't be faster because there's literally no zeros in it. It's a dense matrix. It's a packed dense matrix. So and the computation is necessarily very slow. Okay. However, that's because I'm running it on my CPU. I could run it if I have a powerful GPU available. I could run it on a GPU instead. And again, like I said, GPUs are custom designed. The hardware is designed to do linear algebra, vector, and matrix operations very, very, very fast. And it's got hundreds of cores with which to do vector multiplications and matrix multiplications. So it should be considerably faster than using your CPU with a couple of exceptions. Nowadays, a lot of CPU manufacturers like Intel, they are releasing libraries that make matrix operations on a CPU extremely fast. Okay, so some of you may be if you're interested in that, email me. I'll tell you more about those libraries. You can install them on your computer, and your CPU will be if you set it up correctly, it'll make your CPU really fast. Anyway, it took almost 1 minute to multiply these two matrices together on my CPU. I'm going to use a library called GPU, and I have to ask it, what are my GPUs available? And it tells me that I've technically got three processors that it could use. One is my CPU. Another is an Intel integrated GPU that it's a GPU that is actually integrated into the CPU. Apple does that. It creates like a CPU GPU combination, but this is not a fast GPU. This is a fast GPU for consumer grade, not for gaming or something like that, but for non-gaming purposes, this is a fairly fast GPU that comes with Macs at least a few years ago. So actually Macs that are a few years old come with two GPUs, but one of them is truly a fast GPU. The other is an integrated GPU that's not so fast. So GPU number 3 is the one I'm interested in. So I'm going to tell it, I would like to use GPU number 3 because that's the fastest one I've got. And now the GPU library allows me to create a special type of matrix, which is called a GPU matrix. These are matrices which will be computed purely on the GPU, okay? And now I'm going to create two GPUs, which are based on the same matrices I had before, matrix A and matrix B, which were 3000 by 3000. I'm going to convert them into GPU matrices called GPU A and GPU B, okay? And this time, let me run the GPU operation. And I got a beat. Oh, it's done. Instead of 65 seconds, it took 2 seconds to run. So a powerful GPU is really powerful at running linear algebra like vector math and matrix math. Okay. So if you have a powerful GPU, you may consider the GPU package. However, I've got some bad news for you. Okay. Well, one bad news, which is not terribly bad, is that the results that your CPU produces and the results that your GPU produce are going to look very similar, but not to maybe to the first 10, 20 decimal places, but they will have floating point errors at different places. So your GPU and your CPU will not have the same answers to the 20th decimal place or so, okay? Like at some point, the numbers will deviate. This is a problem with binary representation of math. We talked about that previously. This is not the bad news. The bad news, and I'm really sad to say this library called GPU-R is no longer available on CRAN. You have to install it off of GitHub. So if anyone's interested in using it, contact me. And the person who wrote this library isn't really maintaining it full time anymore, so it's not being updated anymore, which makes me want to cry. But it's still workable, but it's really a pain in the ass to install. I couldn't install it on Linux. I was able to install it on my Mac with a little bit of struggles. So don't depend on everyone having it, but if you're just running it on your computer, you might be able to avail it. You might be able to avail it. So I just want to let you know that it is something that's possible to potentially avail, okay? But again, I'm hoping in the coming year, it'll be re-maintained by that person or somebody else, okay? But GPU operations is possible. And again, if you're doing very low level linear algebraic operations, you might want to take advantage of a powerful GPU. Moving on, I want to get finished in the next 20 minutes, or next 10 to 20 minutes. I want to wrap this up. 10 minutes, okay? Oh, this is my last topic, I think. I want to let you know that RStudio is an application that you're right now running on your computer. RStudio can, for those of you, however, let's say you're going to go into a corporate environment, into a company, you can run RStudio not just on your personal computer, you can run it on a central server for everyone to use. So everyone doesn't need to install RStudio themselves. You can install it on one central machine and everyone can log into that machine and use it, okay? So there are versions of RStudio, which is called RStudio Server, and this is, and it's free. It's actually free, and you can install it on Unix machines. I think it's only available, as far as I know, maybe other, well, if you go to the RStudio, just go search for RStudio Server. Maybe you can install it on Mac or Windows, but typically servers are running Unix. You can install it on different types of Unix machines. And then if you want to use RStudio, you can access RStudio on that server over the internet. So this is my browser, and here is RStudio running in my browser. This is like, all I have to do is I've got to access my machine on a certain port, okay? And then, and this is a server that my institute runs, my department. We have a computational server. And hey, where am I? Where am I? This is not the file I want you to play with. And so on this server, um, oh, this is the code I want to play with, I guess, I suppose. Okay. Um, I think, okay. This is a server that we're running. I hope the parallel, I think I installed the parallel library for it. Okay. Your experience will be is quite. It looks exactly like RStudio, so it should be a very similar experience to RStudio, but it's running in the browser. Okay, we installed it on a server because we set up a special server, which has, oops, num cores, which has 32 cores. So it's an extremely powerful computational server. All right, and it allows us to kind of like run. Excuse, it'll take a while to set up the cluster, and and once the cluster is set up, it'll run the bootstrap. Okay, so now it's running the bootstrap. Bang, that was fast because it was able to run that those 6,000. I think it took like, I don't know, 17 seconds on my computer. It took less than 1 second, I think, on this 32 core beast. Yeah, it took less than 1 second to run on this beast, okay? Because I'm not running Zoom on it, okay? All right. So yeah, you could, if you're doing heavy computational stuff, and you're in a company that has the money, you may invest in buying a server on which you want to run your computation, and you can just access it over the web, all right? And you can upload your files, open up projects, and kind of work on it. It looks exactly like RStudio, all right? It is RStudio running on a server. You just access, run it over a browser. Okay, so that's called RStudio Server. For ISS students, you have access to this. We have a computational server for you to use. For others, if you're in an institute or a department or a company, you may invest in a machine which is powerful, has a powerful CPU, GPU, etc., and you may want to install RStudio Server on that, and then people can access it remotely. Okay, all right. Okay, that is everything I want to cover for this 17th and last session of BSCS. It's been a total thrill for me to teach this semester. I say that every year, but I mean it every year, okay? It's been a thrill for me to teach this class. Um, and I love teaching this class because it's often the first time many students are encountering programming. It's the first time many students who know programming are entering the world of serious computation. So it's really cool to see the joy in all the students as they're kind of picking up on these things, and how much many of you enjoy these kind of topics. I love teaching this class, okay? And I just want to leave you with a few thoughts. The first is that, I hope you all enjoyed the stuff we talked about, resampling and simulating, and and um, and when we do analytics, it's not all about just running a function, finish my analytics. I want to encourage you all to use simulation tools, resampling tools, all kinds of simulation things to enhance your abilities and enhance your analytics. So that was a big part of the semester, is to bring basic simulation and resampling simulation strategies that you can all use. Okay, so that's one thing. The second thing is, I want you to all consider using interactive visualizations. So over the semester, I used a lot of visualizations that were interactive. I used visualizations for, power and error analysis, for regression, for PCA maybe. So there was a whole bunch of interactive visualizations we created. So I want to encourage you to create more interactive visualizations, not just visualizations you print out on a paper and you send to somebody. I often find if you create a visualization that people can play with, they get so much more excited about it. Okay, so I hope that's another tool in your arsenal. I want you to think about statistics, not just about some formulas, but I want you to think about stats and computation from a geometric point of view. So one of the things I love introducing students to in this semester is problems like correlation from a geometric perspective. I think geometry is a powerful way of looking at data and analysis, and it's kind of it has a dualism with statistics. They're often trying to do the same thing and expressing it in different ways. So I really encourage you, if you're going into a world of analytics and data science, um, learn more geometric concepts, because geometry is a beautiful way, an alternative universe to statistics, and they often try to do the same things. And if you look at very, very, very high end data scientists, a lot of them really learn advanced geometry and topography and things, because that's becoming increasingly powerful and important in very advanced forms of machine learning, particularly like multi-tier neural networks and things. A lot of the time, we're able to now describe a lot of these problems geometrically rather than statistically. So it's a very powerful thing to have in your arsenal. So get familiar with geometry again, okay? And the last thing I want to mention is you're gonna learn how to use a lot of packages and tools over your career. Don't be afraid to write your own tools, okay? If you find you're doing an analysis again and again and again, don't think that the people who create packages out there are smarter than you. They're not. A lot of the time, they're just older than you, so they made those packages before you. My students and I found there's a lot of stuff we're doing that we can wrap up and create our own packages and publish them. And people around the world are so excited. We've got hundreds, or at this point, thousands of people using just Seminar. And that's just one package we've published. We're working on several other packages now. And it's so exciting to see people from all over the world using our tools. All right. So I want you to encourage you to think of yourself not just as a data analyst, but also as a tool maker. You can be somebody who makes tools that other people use. And when you do that, you become famous really quickly. You'll have people from all over the world contacting you all the time and saying, hey, would you please come give us a talk? Would you please, help us out with this? And you'll become uh, internet famous at least. Okay. So I want to encourage you all not just to use programming to solve basic data problems, but start making your own tools. If you're making visualizations which are unique, package it up and share it with people so that other people can do what you're doing. Okay. So I want you to move your thinking from being a tool user and to becoming a tool maker. Okay. So these are the important messages I just kind of want to leave you with this semester. So back to my main slide here, if I can go back to my slide. So you may be wondering, what the hell are these little arrows coming out of week 17? It's you. You are the vectors coming out of this class, okay? And I don't know which direction you will each go to. I don't know what your magnitudes will be either. But I'm excited to see how your career unfolds. So do stay in touch with me, especially if you're going in a data science or computational direction in any way, shape, or form. I'd love to hear back from your stories. All right. You will not believe how many things I'm teaching in this class, which were inspired by students who left my class and came back to me and said, hey, in my company, we're doing this and that. And I'm like, cool, tell me more. Okay. Um, so yeah, to the sky with you guys. All right. So I encourage you all, stay in touch with me, stay in touch with each other. Let's have an amazing experience introducing computational tools into our career, whatever your career might be. And I think a lot of you will be surprised to find you'll be entering maybe directions in research or industry where people are not applying computation as much as they could be. And you could be the person who introduces your company or your institute or your department or your field to more computational techniques. And people will be grateful to you. They'll be afraid of you, which is great, right? When you walk in through the door, they'll be like, "Oh crap, there's that guy." All right, so you'll get a lot of attention and respect and fear, all good things to have. All right, and I hope you have a lot of fun using computational techniques and learning more and more about computation. And please get back in touch with me and tell me, hey, you know what else I learned? I learned this thing or that thing, and it's such a joy to be able to share that with students in future. All right. And maybe in future, I'm hoping to hold in future years a series of talks by alumni of my class, because now there's like hundreds of people who've taken my class, And I'd like to have some kind of online virtual sessions now that we're all going virtual, where I bring back alumni of previous semesters to give talks about cool stuff they're doing with computation. And if I get around to doing that, I'll invite you all as an alumni of this class to kind of to keep in touch and to share things with each other. Okay. So with that, thank you all. Have yourselves a great summer. Stay safe. Be smart. And happy hacking. All right. Thank you all for joining this semester. And please do stay in touch and do take care of yourselves. Okay. Bye bye. See you all. Thank you so much. Thank you. All right. You may log off. I'm going to end the live stream and I'm going to end the